Hey, we're really jumping into something fascinating. AI agents.
Yeah, it's a huge topic right now, moving fast.
Definitely. These aren't just simple programs anymore, are they? They feel like, well, autonomous entities.
That's the key word, autonomous.
So our mission today is to kind of break down what makes these agents tick. You know, from the basics right up to the really complex stuff.
Consider it your crash course, get you up to speed quickly.
Exactly. Because understanding how they sense, think, and act, well, it's becoming essential for anyone working with AI today.
Couldn't agree more.
Okay, let's unpack this. So first things first, if we're talking AI agents, what is an agent fundamentally?
Right. So think of an agent as basically an autonomous entity. Could be software, could be hardware.
A self-directed worker is how I've heard it put.
That's a good way to think about it. Its job is to do things, take actions in some kind of environment to reach specific goals.
And autonomy is the big deal here.
Absolutely. It operates without someone constantly telling it what to do. It reacts to changes. It's proactive in trying to meet its goals. And yeah, it's goal-oriented.
And they range from simple to complex, right?
Oh, totally. From like a basic thermostat that's technically a simple agent all the way up to these really sophisticated learning systems we see now.
Okay, so you mentioned the environment. They need a place to operate.
Exactly. The environment is just, well, the world the agent lives and acts in. It provides all the context.
It's the stage for their actions.
Perfectly put. And that stage can be physical, think a robot moving around a room or a drone outside.
Or digital.
Or completely digital, yeah. Like a chatbot interacting with users, or maybe an agent managing cloud resources, or even an AI character in a video game.
And the type of environment matters a lot, I assume? Like, is it always changing? Can the agent see everything?
Huge impact, whether it's static or dynamic, fully observable or only partially. That really shapes how the agent needs to work.
So the agent's in its environment. How does it figure out what's going on? Perception.
That's it. Perception is how it senses its world, interpreting signals, data, whatever comes in from the environment.
Crucial for making decisions, I bet.
Absolutely vital. It needs to build some kind of internal picture and understanding to make informed choices. Without good perception, it's flying blind.
And where does that info come from? Sensors?
Yep. Physical sensors like cameras, microphones, maybe LiDAR.
LiDAR, that's the laser thing.
Yeah, it uses lasers for really detailed 3D mapping. Or touch sensors. And in the digital world, it's things like API responses, database info, user text, system logs.
Lots of raw data, probably needs cleaning up.
Often, yeah. Pre-processing is usually needed before the agent can really make sense of it. Noise reduction, formatting, that kind of thing.
Okay, so all this perceived data feeds into the agent's state. What is that exactly? Its internal snapshot.
Pretty much. The state is the agent's current understanding, what it knows about the environment and maybe about itself right now.
Built from perceptions.
And its own internal logic, yeah. It includes what it's currently seeing, what it remembers, what its goals are.
And even things it thinks are true. Beliefs.
Exactly. Inferences it makes about stuff it can't directly see. A solid, up-to-date state is critical for any kind of complex thinking or planning.
Makes sense. And that leads us to memory. Just like us, they need to remember things.
Oh, absolutely fundamental. Memory lets the agent store information over time, past events, actions, what it saw.
Gives it context, helps it learn.
Precisely. Provides context, supports learning from past mistakes or successes, lets it adapt.
And they're different kinds. Short-term, long-term.
Right. We often talk about short-term memory, sometimes called the context window, especially with LLMs. That's like its immediate scratch pad for the current interaction.
Okay, what it's thinking about right now.
Exactly. Then there's long-term memory. That's for persistent storage, think databases, often vector databases these days.
For vector databases, for meaning-based search.
You got it. And this often involves RAG, retrieval augmented generation.
RAG. Okay, tell me more. How does that work?
So RA is like, imagine the agent has a massive library of past experiences or knowledge. RA is the super smart librarian that instantly finds the exact right book, the most relevant piece of info from that library to help with the current task.
Instead of just relying on its immediate thoughts.
Exactly. It pulls in relevant long-term memories to augment its current reasoning. This can include episodic memory-specific past events or semantic memory general facts.
Got it. Okay. Agent, environment, perception, state, memory. Now, the brain. Large language models, LLMs. That's where they come in.
That's often the core, yeah. Models like GPT, Claude, Gemini, these huge neural networks trained on tons of text and code, they act as the central intelligence for many modern agents.
They do a lot, right? Understand language.
Natural language interface is key. Understanding prompts, generating responses, but also reasoning, making logical deductions.
Planning, too.
Yep. Breaking down big goals into smaller steps.
Yeah.
And even selecting the right tools for the job.
Tools.
Yeah.
We'll get to that. But first, LLMs don't just know everything relevant, right? They often use a knowledge base.
Correct. A knowledge base is basically a curated collection of information the agent can tap into.
More organized than just raw data.
Usually, yeah. Structured data like facts and rules, or unstructured stuff like documents, articles, FAQs. It's information the agent can reliably use for reasoning or answering questions.
And this ties into RAG again.
Often, yes. Especially with RAG, that knowledge base might be in a vectored database, making it easier to search semantically finding info based on meaning, not just keywords.
Cool. Now, one technique I find really interesting is chain of thought. It helps the LLM think better.
It does. Chain of thought is where the LLM explicitly writes out its reasoning steps.
Yeah.
It breaks down a complex problem step by step before giving the final answer.
Like showing your work in math class.
Exactly like that. And the benefits are huge. Better accuracy, especially for problems needing multiple steps.
You can see how it got the answer. More transparent.
Right. You see the logic. Prompts often include something like, let's think step by step to encourage this.
Okay, and building on that is something called React. Reason and act.
Yeah, React is really clever. It interleaves the reasoning part, the chain of thought, with taking actual actions in the environment, often using tools.
So it's not just thinking then acting. It's a cycle.
It's an iterative loop. Thought, action, observation, thought. The agent thinks about what to do, maybe uses a tool.
Like a search engine.
Could be. Then it sees the result, the observation, and thinks again based on that new information, deciding the next action. It's much better for dynamic situations where things change.
That makes sense. It lets the agent react to what's happening. Now, you mentioned tools a few times. These sound critical.
They're absolutely crucial. Tools, sometimes called functions or plugins, are external things the agent can call. APIs, software functions, specific modules.
Extending what the LLM can do on its own.
Massively. This is what grounds the LLM in reality. It lets it interact with the current world or perform complex calculations. It gives the brain arms and legs, essentially.
So examples, like checking the weather.
Exactly. Calling a weather API, using a calculator, searching the web, querying a database, running code, accessing specific company tools. The possibilities are huge.
So after all this, perception, state, reasoning tools, we finally get the action.
Yep. The action is the concrete step the agent takes, doing something in its environment or its internal system.
The result of all that thinking.
It's the culmination, yeah. How it actually achieves goals and changes things.
And that could be anything. Replying to a user.
Sure. Replying to a user, updating a database, moving a robot arm, sending an email, calling one of those tools we just talked about. It's thought made real.
Okay. Before we jump into more complex systems, maybe quickly touch on the simplest type. Reflex agents.
Good point. Reflex agents are the baseline. They just react based on simple pre-programmed rules. If X happens, then do Y.
No memory. No learning.
Nope. No internal model of the world. No memory of the past. Just direct stimulus response. Think of a very basic thermostat or a simple obstacle avoidance rule in a robot. If sensor detects obstacle, turn left.
Very different from the LLM-powered agents.
Night and day. Useful for simple automation, but our deep dive really focuses on agents that go beyond pure reaction.
Right. So moving beyond Reflex, we get into planning. This is about looking ahead.
Exactly. Planning is the agent figuring out a sequence of actions to reach a longer-term goal. It's about strategy, anticipating consequences.
Not just reacting to the immediate situation.
Correct. This involves things like breaking down big goals into smaller ones, goal decomposition, finding the best sequence of actions, maybe even planning for things going wrong, contingency planning.
So it's much more strategic.
Definitely. Allows agents to tackle complex tasks over time.
Now, when you have lots of parts working together, tools, maybe smaller agents, LLMs, how do you manage all that complexity? Is that orchestration?
That's precisely it. Orchestration is like being the conductor of an AI orchestra. It manages the complex workflows, coordinating all the different components.
Making sure the LLM talks to the right tool, gets the data, handles errors.
All of that. Managing the sequence, coordinating the parts, handling errors gracefully, maybe even changing the plan on the fly. It's what allows these agents to perform really complex multi-step tasks smoothly.
And sometimes one agent needs to pass the job to another, or even to a human. Handoffs.
Yes, handoffs are crucial for smooth operation, especially in complex systems or when humans are involved. It's about transferring the task, the context, the responsibility seamlessly.
So you don't have to repeat yourself.
Exactly. Avoids losing context. Think about a chatbot escalating a complex issue to a human agent, or maybe one specialized AI agent passing its results to another for the next step. Good handoffs are key for efficiency.
Okay, so what happens when you have multiple agents working together in the same environment? Multi-agent systems, or MAS?
Right. A multi-agent system is just that. Two or more agents interacting in a shared space.
And they might cooperate. Or compete.
Both are possible. They might work together on a shared goal, or they might compete for limited resources, or they might just need to coordinate to avoid bumping into each other, literally or figuratively.
Why use multiple agents instead of one big one?
Sometimes problems are too big or too distributed for one agent. MAS allows you to break down the problem, use specialized agents, and handle more complexity.
Interesting. And there's a specific type of MAS called a swarm. Sounds like bees or ants.
It's directly inspired by them. A swarm involves many relatively simple agents. Each one follows basic local rules.
No central controller.
Nope, it's decentralized. Agents interact locally with their neighbors or their immediate environment, but the magic is that complex, intelligent behavior emerges at the group level from all those simple interactions.
Wow, so the group is smarter than the sum of its parts.
In a way, yes, and they tend to be very robust. If a few agents fail, the swarm can often carry on. Think of drone swarms mapping an area together.
Okay, that's pretty advanced. And even more so is agent debate.
Yeah.
Agents arguing with each other.
Arguing constructively, let's say. Agent debate is a technique where multiple agents critique each other's plans, solutions, or reasoning.
Like AI peer review.
That's a good analogy. Or like a structured debate. You might have agents with different viewpoints or expertise challenge each other's proposals.
Why do that? To find flaws.
Exactly. It improves accuracy by catching errors. It can enhance creativity by exploring different angles. It helps reduce bias. And it makes the final solution more robust because it's been stress tested.
So you get more trustworthy results.
That's the goal. Really powerful for complex decision making.
Okay, with all this power and complexity, how do we actually know if these agents are working well and safely? That must be evaluation.
Absolutely critical. Evaluation is the whole process of systematically checking how well an agent performs.
Defining metrics, running tests.
Right. Defining what success looks like. Metrics like accuracy, efficiency, task completion rate, maybe user satisfaction. Then running tests, analyzing the results.
Why is this so important?
Well, for obvious reasons. To improve the agent, iterate on the design, but also crucially for safety and reliability. You need to know it does what you expect and doesn't do harmful things you don't expect.
Makes sense. And finally, for agents to really get smarter over time on their own, we need a learning loop.
The learning loop is fundamental for true long-term autonomy and intelligence. It's the cycle where agents adapt and improve based on experience.
Not just static programming.
No, it's dynamic. The agent takes an action, observes the outcome, gets some kind of feedback, maybe explicit, maybe just seeing the result, and then it learns. It updates its knowledge or strategy.
Which then influences its next action.
Precisely. Action, observation, feedback, learning adaptation, new, hopefully better, action. It closes the loop, enabling continuous improvement without constant human intervention. It's how AI genuinely learns from doing.
Wow. Okay, so we've gone from basic reflexes all the way to agents that can plan, use tools, work together, debate, and learn continuously. It's quite a journey.
It really is. The progression is stunning when you lay it all out. From simple reactive rules to systems that genuinely perceive, reason, strategize, act, and evolve.
It feels like a fundamental shift.
I think it is. It changes how we even think about solving problems with computers. We're moving from tools we operate to partners we collaborate with, in a sense. Dynamic, adapting partners.
So here's something to think about. If AI agents can perceive, reason, plan, act, learn, and even debate, what does that really mean for the future? How we solve problems?
Yeah, how does it change our own roles when we have these autonomous systems constantly learning and refining their view of the world alongside us? What does decision-making look like then?
So what does this all mean? We leave that with you to ponder.